What if your map detecting skills decided whether you got the job? Number of islands is a pattern mastery 100 must solve, and a recurring favorite at Google, Meta, and Amazon for Grid DFS/BFS mastery. Over 30% of candidates get lost handling visited cells or edge cases. If you can handle this, you'll be ready for any connected component problem in an interview. Let's solve number of islands using the basic method, breaking down the problem step by step, so you can handle any matrix traversal with confidence. Given a 2D grid of ones, land, and zeros, water, count the number of islands, groups of horizontally or vertically connected land. An island is surrounded by water and is formed by connecting adjacent lands. 2D grid of characters 1, land, and 0, water, integer, total number of islands. Think about processing satellite images to count disconnected land masses, or identifying clusters in a social network or a game map. Interviewers might ask, how would you efficiently find all clusters or groups in a connectivity map? What's tricky? You must explore all connected ones for each island and ensure each cell is counted only once. Need to avoid double counting or missing isolated cells. Both DFS, recursion or stack, and BFS, queue, work, but must mark cells as visited. Loop through every cell in the grid. When you find a 1, it's a new island. Increment your count. Use DFS or BFS to mark all connected ones as visited. For example, change to 0 or mark in a visited set. Repeat until all cells are processed. Let's clarify. For each new one, you flood fill the island, ensuring every connected cell is covered before moving on. 4 directions per cell. Up, down, left, right, no diagonals. Edge cases. Empty grid, return 0. One giant island, should count as 1. Many tiny islands, single cells, count each. Initialize island count to 0. Loop through all grid cells. If cell is 1, run DFS/BFS from this cell to mark all connected ones. Increment island count for DFS/BFS. For each cell, if in bounds and 1, mark as visited, 0 or visited set. Recurse or queue all 4 directions. Return island count. Solution 1 uses DFS to solve the number of islands problem. This comment is just a label for us humans. Creates a class solution, a container for our function counting islands in the grid. Define new islands. Taking grid, a 2D list, 1 equals land, 0 equals water. Goal, count separate chunks of connected land, islands. Check if the grid is empty or missing. No data, no islands. Return 0 immediately if the grid is empty. Grab grid dimensions, m equals rows, n equals columns, for safe navigation. Initialize count to track discovered islands. Increment each time a new island is found. Define DFS, depth first search, to explore and sync land starting from I, J, so we don't count it again. Safety check, stop if out of bounds or current cell is water/already visited. Return immediately if the cell is invalid, path is water, out of bounds, or visited. Mark current land as 0 to indicate visited, preventing double counting. Explore cell below. Explore cell above. Explore cell to the right. Explore cell to the left. Together, all 4 calls fully traverse the connected island. Scan each row index I from 0 to M1. Scan each column J from 0 to N1. Double loop visits every cell once, OMN. If current cell is 1, we found unvisited land, a new island. Increment count for this new island. Call DFS to sync this island. Mark all connected land as 0, ensuring no part is counted again. Each land cell is visited once, OMN. Return count, total number of separate islands, connected 1 groups. Each cell is visited once in the double loop. DFS touches each land cell once. Time complexity, OMN. Space, recursion stack, worst case OMN. The algorithm scans the grid for new land cells, then DFS fully explores and syncs each island so it's counted exactly once. Efficient, simple, and elegant. Let's test our function. Each cell is 1 for land or 0 for water. We count islands, connected ones touching up, down, left, or right. BFS finds the first one, increments the island count, and spreads through all connected ones, turning them into 0. Here, all ones in the top 3 rows form 1 island. The rest are 0, so no new islands are found. The output is 1, matching the expected value. BFS correctly identifies and clears the entire island efficiently and reliably. Solution 2 uses BFS to count islands. This comment just labels it for clarity. Import deck from collections, a fast queue for BFS to explore neighbors level by level. Start the solution class, container for our island counting method. Define new islands, accepting a grid of 1s, land, and 0s, water. Goal: count separate islands. Check if the grid is empty or missing. If no grid exists, return 0 immediately. Get grid size, m equals rows, n equals columns, for safe navigation. Initialize count equals 0. Increment when a new island is found. Loop over rows and columns. Together, these loops scan every cell once, om times n. Found unvisited land, start of a new island. Increment island counter. Sync this cell immediately to avoid recounting. Start BFS with a queue containing this cell. BFS will sync all connected land. Loop while queue has cells. Pop next cell from the front. BFS processes earliest added items first. Check all 4 directions: down, up, right, left, 1 per neighbor. Compute neighbor coordinates. Neighbor is inside grid, is land, an unvisited part of same island. Sync neighbor to prevent revisiting. Add neighbor to BFS queue to continue exploration until the island is fully sunk. After scanning and BFS syncing all islands, return count, the total number of islands. Grid scanned once, om times n. Each land cell visited once and sunk, om times n. Total, om times n. Very efficient. Algorithm scans unvisited land, then BFS explores and syncs the entire island. Efficient, simple, and elegant. Let's test our function using this case 2 grid. Each cell is 1 for land or 0 for water, and we're counting how many separate islands appear. BFS works like this. When it finds a 1, it adds +1 to the island count, then spreads through all connected land cells, turning them into 0 so they're not counted again. In this grid, BFS clears the top left island first, then it finds a single isolated one in the 3rd row, that becomes the 2nd island. Finally, it reaches the 2 connected ones in the last row, the 3rd island. That matches the expected result, 3. Our BFS correctly identifies all 3 separate landmasses. Let's have a quick recap. We're given a 2D grid of land and water, and our goal is to count how many distinct islands exist. Each island is made up of connected land cells that touch horizontally or vertically. Conceptually, this problem is all about grouping and identifying isolated clusters within a matrix. The main challenge here is avoiding double counting. When we find land, we need to make sure all connected cells are explored and marked before moving on. Both DFS and BFS work here. DFS tends to feel more natural in interviews since it mirrors the floodfill idea. The trick is systematic marking. Once a cell is visited, we never process it again. We loop through every cell in the grid. When we hit a 1, that's the start of a new island, so we increment our counter. From there, we trigger a DFS or BFS that explores all connected land, marking each as visited or converting it to water. Once that's done, we continue scanning the grid until all cells are processed. We structured our DFS cleanly, checking boundaries, marking visited cells, and exploring 4 directions from each one. The entire process ran seamlessly on LeetCode, and the code executed without any errors. After running the solution, every test case passed perfectly. From empty grids to single massive islands, the logic held up, no missed cases, no overlaps, all outputs matched expectations. The key takeaway: mastering grid traversal and marking visited cells is the foundation for countless graph problems. Once you can flood fill confidently, you can handle any connectivity or component counting challenge an interviewer throws your way.